Already? Yeah. Okay. All right. Good morning. So today I'm going to talk about section 9.2. We had a couple of days of 9.1, which was the molecular geometry or Vesper theory. And so I spent a couple of days on that because it is a somewhat involved theory, and you really have to kind of go through a lot of analysis. But just to sum it up, what you're doing is you're looking at the central atom and you're taking your surrounding atoms, and then you're essentially just counting how many surrounding atoms there are and how many lone pairs there are. And then you're just using the table 9.2, to figure out what the shape is. And then when you figure out the shape or geometry, you want to pay attention to what the angles are, right? There's several angles. There's the 90, there's the 180, there's the 120 and the 109.5. 104.5 and 107. Okay, so there's like 7 angles there. Okay, so we're actually going to continue doing it in a sense because we're going to talk about 9.2 today, which is predicting predicting molecular polarity. So we talked about bond polarity back in chapter 8 when we did electronegativity. But often the bond polarity doesn't match up with the molecular polarity. And the molecular polarity is actually more important to us. We want to know whether a molecule is polar, not whether a bond is polar. So we only looked at electronegativity and bond polarity on chapter 8. Today, we're going to put it together with our Vesper theory and figure out whether molecules are polar. The importance of this is that if a molecule is polar, it tends to boil at a higher than expected temperature. So for example, we all know about water, right? Water boils at 100 degrees C. If you look at other molecules that are similar in size to water, meaning like 3 atoms, like H2O, and they're nonpolar, they tend to boil into a gas below 0 degrees C, actually below 0, so below the freezing point of water. An example of that is carbon dioxide. If you think about it, carbon dioxide is CO2, right? 3 atoms. It actually boils at negative 80 degrees C. So if carbon dioxide behaved like water, it would liquefy on the surface of the earth, right? It would be a liquid on the surface of the earth, but we don't see liquid carbon dioxide. Carbon dioxide is a gas. In fact, carbon dioxide, the only way you really see it is as dry ice. Dry ice, they call it dry ice because it's not wet, right? It's not liquid. Dry ice is frozen carbon dioxide, and it's made in a pretty cool way. You pressurize it, and it undergoes a phase change into the solid phase, and then you've got this block. It looks like ice, a little bit like ice. It's softer than ice, but it's essentially solid carbon dioxide. But it will just vaporize, right? It undergoes what we call sublimation at room temperature. So dry ice only sticks around for a few hours, and then it's a gas again, right? Water, on the other hand, is a liquid at room temperature. You have to get it up to a pretty high temperature to boil it. And that is directly connected to molecular polarity. Because water is highly polar, that means that it boils at a high temperature. Molecules that are not very polar, they boil at lower temperatures. Okay, so let's take a look at this idea. So we're looking at, this is section 9.2, and we're going to call this molecular polarity. Okay, so let's review real quick. What makes something polar or not, right? So what we said was the oxygen-hydrogen bond was polar, that there was a small positive charge on the hydrogen and a small, remember the symbol delta, the lowercase delta? Small negative charge on the oxygen. That means small, meaning it's not a charge of -1 or +1, it's a charge of maybe -0.1 or -0.2 or -0.3, something like that. Okay. So what gives rise to the fact that this has charges, right? And we also represented it like this. We said, hey, let's just say there's a negative end here and a positive end here. We called that a bond dipole, right? Right, and we said that it had electrical properties, right? It had to do with alignment of these dipoles, okay? And we would call this a polar bond. Okay, so it's still covalent, but it's polar. Now, what gives rise to it? Electronegativity differences, right? We said that the electronegativity of oxygen was 3.5, and the electronegativity of hydrogen was 2.1. So we said that if you looked at the difference, here I'll use a delta for difference, the difference in those two electronegativity values was pretty large, 1.4. That's a very big difference in electronegativity, right? We said that if it was greater than 2, it would actually be an ionic bond. But if it was greater than 0.4, or if it was 0.4 or greater, it would be a polar bond. Well, that's a very big difference, 1.4. So that's what gives rise. Essentially, what happens is the oxygen atom is so attracted to these electrons in the bond, that it pulls those two electrons toward itself, away from the hydrogen. You can think of electronegativity as this sort of tug of war. The one that has more electronegativity, a larger value, is better at pulling the electrons toward it. So the electrons migrate over towards the more electronegative element. So the result of that is that the less electronegative atom, or the electropositive atom, is more positive, and then the one that's more electronegative is negative. So you just use those values. So an example of an alternative would be, what if you had phosphorus and hydrogen, a bond between those two atoms? Well, the electronegativity values are pretty close. They're like 2.1 and 2.1. Some tables will put them at 2.2, but they're essentially the same. So that means those two nuclei, those two atoms, are tugging on the electrons in the bond, and they're equal at pulling the electrons. So it's equal, right? So what you get is your difference in electronegativity is very small, maybe even equal to 0. It's probably not exactly 0, but it's pretty close to it. Yeah, 0, so it's nonpolar, right? There's no dipole there. Okay, so that's easy. That's just looking up the values of the electronegativities and determining whether a bond is polar or not. The one that is more electronegative will have the negative charge. The bigger the difference, the more polar the bond is. So when you start getting up to differences of 1, that's a pretty big difference, and it's going to be pretty polar. You get up to differences of 1.5, that's really, really polar. In fact, OH is a pretty polar bond. 1.5 is even more so. We don't really quantify it. You can't really say, oh, it's going to be exactly this polar. We're just sort of judging it qualitatively. Is it a really small difference? Is it a moderate difference? Or is it a very large difference? So we gave you a kind of set of rules that if it was greater than 2, it's ionic. If it's less than 0.4, it's nonpolar. And if it's between 0.4 and 2, it's polar, but more polar as you get to larger, okay? So it's not exactly quantitative. It's what we might call semi-quantitative, meaning that the larger the number, the more it is, the smaller the number, less is, but it's not like a bond enthalpy. You can't say it's exactly this strong, or a bond length, it's exactly this big. It's something that's you're just sort of judging it, okay? So now let's look at molecular. So the issue of molecular is an interesting one. So let me show you 2 molecules. I'm going to pick 2 molecules to compare. The first one is carbon dioxide, and the second one is water. And I'm going to show you what their boiling points are. And this is at 1 atmosphere. So the temperature that something boils at depends on what the air pressure is. It depends what the pressure of gases is. So this is at 1 atmosphere, which is the atmosphere we exist on. So the boiling point, TB, is around negative 80 degrees C. It's really, really low at 1 atmosphere. For water, on the other hand, it's 100 degrees C. That's a very large value, right? That's a big difference. Even though each molecule has the same number of atoms, it's even more interesting than that. So here's what I'm going to do. Oops, I'm sorry. Here's what I'm going to do. For carbon dioxide, I'm going to draw its Lewis structure first. You'll note that in chapter 9, pretty much everything starts with the Lewis structure. So there's carbon dioxide. Oops, sorry. I kind of jumped ahead there. Okay, so carbon is the central atom, and you have 2 surrounding oxygen atoms. Okay, let's count up the valence electrons. Oxygen is in group 6A, carbon is in 4A. So that means we have 6 valence electrons plus 4 plus 6. So that's 16 electrons. We've already used 4, so we're down to 12. So we put them on the surrounding atoms. And now we're done, except the carbon only has 4, right? So what do? We push a pair from the atom that has 8. And that's going to give carbon 6, but it won't give it 8. So what do we do now? Push a pair from another oxygen. You might argue, well, why not push 2 pairs from one of the oxygens and none from the other? And the answer is you could do that. The problem with that is that you get a formal charge of +1 on one of the oxygens and -1 on the other. But if you push 1 pair from each, you get formal charges of 0. So we're looking for 0 formal charges. So that leads us to a double bond. Oops, sorry. Actually, I can fix this. A double bond between the carbon and each of the oxygens. Okay, so there's your carbon dioxide. Let's do the same thing for water. Let's draw, we've done the water pretty easily, right? We know how to do that one. Hydrogen is in group 1A, oxygen's in group 6A, hydrogen's in 1A, so you got 1 plus 6 plus 1, that's 8. We've already used 4. That leaves us with 4 remaining, so we put them on the oxygen, and there we go. Octet for oxygen, duet for hydrogen. So there's our Lewis structure there. So let me bring this one down. This one's very polar. Now, how do we determine that? Well, what I'm going to do is I'm going to create a new slide. I'm going to show you the electronegativity values. The electronegativity value for oxygen is 3.5. For carbon, it's 2.5. And for oxygen, it's 3.5. For hydrogen, it's 2.1. For oxygen, it's 3.5. And for hydrogen, it's 2.1. Okay. So if you compare, if you look at the carbon oxygen, that's a difference of 1, right? So there is a difference in electronegativity there. There's certainly a difference in electronegativity here. We already know that. 1.4, 3.5 minus 2.1. So they both should be polar, right? The bonds are polar. There's no question about it. The carbon-oxygen bond is a polar bond. Maybe not as polar as oxygen-hydrogen, but they are both polar. However, overall, this molecule here is non-polar. This molecule here is very polar. So we have to ask the following question. If we're claiming that electronegativity is how you determine, then why is carbon dioxide nonpolar? And that has a huge effect on its physical properties. It boils at a very low temperature. It's not when it is a liquid, it's not very viscous. It's only a liquid under extreme conditions. You have to put it into weird conditions to make it a liquid. So how do we explain that? And here's the answer. We have to consider the molecular structure. The molecular geometry affects molecular polarity. Okay, molecular geometry, which we learned in section 1, it will affect the molecular polarity. And here's why. What I'm going to do is I'm going to start with the carbon dioxide. So here's our Lewis structure. Oops. Actually, sometimes you know what people will do, just so I'll show this to you. Sometimes what people will do is they'll actually put the more electronegative atom in red. It's kind of cool. So red is if you've got electrons, right? So it's, since oxygen is more electronegative than carbon, we'll put it in red. Okay. All right, so here's what happens essentially. The difference between oxygen 3.5 and carbon 2.5, sorry, 3.5 and 2.5 is it's a big difference. So essentially what you get is you get a negative charge here, right? And you get a positive charge here. So the oxygen is negatively charged and the carbon is positively charged. And then the same thing happens over here though, right? The oxygen is negative. So in fact, you've got a negative on the right side, you've got a negative on the left side, and then in the middle, you've got a positive charge. Now let's look at the shape of the molecule. Let's take a look. We've got a central atom, and we have two surrounding atoms, right? That's the notation we talked about the last couple of days, AX2. No lone pairs. So what that is linear, right? The shape is linear and the angle is 180. So carbon dioxide is a linear molecule. Now, here's what happens. Dipoles add like vectors. That's the important point of this section. When you add dipoles, they add like vectors. So let's talk just real quickly about what a vector is. A vector is something that has a value, a number, a magnitude, we call it. 30, 60, 0.1, 3 times 10 to the 24th. But it also has a direction component, right? So for example, if I say I'm moving at 30 miles per hour, that's what we call a scalar quantity. It just has a value. We're moving at 30. So you could be moving to the left, you could be moving to the right, you could be moving up, you could be moving down. But if you just say you're moving 30 miles an hour, that's your speed. That's called a scalar quantity. But we also have this thing called velocity, which takes into account the direction. So if I were to say I'm moving 30 miles per hour, this direction, I'm moving in this direction right here, that would be a vector. A vector is the direction, is the magnitude plus the direction. There's two pieces of information there, okay? Dipoles are vectors, which means that they have a magnitude, a size, but they also have a direction. And the significance of that is that when you add vectors, they add according to their magnitude, but they also add according to their direction, okay? So let me compare. Let's take a look at scalar. Scalar would be like atoms. So if I have 3 atoms and I have 5 atoms, I have 8 atoms, right? 3 plus 5 equals 8. That's a scalar quantity. Or energies. Energies are essentially scalar, right? I have 100 joules, I have 200 joules, that would be a total of 300 joules. That's what we did back in chapter 5. 100 joules plus 200 joules equals 300 joules, right? That's a scalar quantity. Vectors would be things like forces. Okay, so if I'm pulling in this direction and someone else is pulling in the opposite direction, right? Here's a force going down and here's a force going up. If they're pulling in opposite directions, what happens? Those forces will cancel each other, right? We all familiar with that, right? So like if two people are pulling on a rope in opposite directions, if they're pulling with the same force, the rope isn't going to move. It's going to be stationary. But if one person pulls with more force, the rope is going to move, right? So the direction is important. If two people are pulling on the rope in the same direction, the rope is going to accelerate in the direction of the forces. So dipoles are the same. They follow the same mathematical relationships that forces do because forces are vectors. So here's what happens. When you have a dipole, so this is linear, right? We already decided it's linear according to Vesper theory. When you have two dipoles that are in opposite directions, okay, so I'm going to represent the vector. That's the dipole. The dipole is represented with a vector. I'm going to put the head of the arrow in the direction of the negative charge and the tail of the arrow in the direction of the positive. And sometimes we do this in chemistry. We put a little line there to remind us that's where the positive is. And the head of the arrow is the negative. So that's your negative there. These two vectors are in exactly opposite directions because the molecule is linear, right? Meaning the negative of this bond is on the opposite side as the negative on that bond. So think of it like forces. They're pulling in opposite directions. And so now imagine if two people are pulling exactly the same force in opposite directions, the net force is 0, okay? So if you add up, I'm gonna use the symbol sum, sigma. Sigma means the total. You're gonna sum them up. Let me write it here. The sum of the dipoles is equal to 0 in this case, all right? So the result of that is if the sum is equal to 0, it's a nonpolar molecule. So even though at the molecular level, each bond is polar, overall, the molecule is nonpolar because the dipoles cancel each other out. So now we have a method for evaluating molecular polarity. Essentially what we do is we look and see, are the bonds polar? If the bonds are nonpolar, the molecule is nonpolar. Okay, you can't have a polar molecule with nonpolar bonds. But if they are polar bonds, now we have to look at the shape of the molecule and evaluate how these dipoles add up. And that's just a geometric issue. If they're in opposite directions, they cancel. If they're in the same direction, they don't cancel, and the molecule is polar. So let's compare that with water. We know water is polar. So what I'm going to do is I'm going to start with the Lewis structure. So there's your Lewis structure of water, right? Let's figure out the shape. The shape is you've got one central atom, two surrounding atoms, but you also have two lone pairs. So remember our symbols that we use for that, two lone pairs. That corresponds to the bent arrangement. And the angle was 104.5 degrees, a little more than a right angle, right? A right angle is 90. Tetrahedral was 109.5, right? So it's a little less than a tetrahedral. So here's the way we could represent this. So there's one bond. There's another bond, right? So it's bent. Not linear, right? So what happens in terms of electronegativities? Oxygen, very large. The second most electronegative element in the periodic table. Remember, fluorine was 4, oxygen was 3.5, nitrogen was 3.0, and chlorine was 3.0, around there. Those are the 4 most. This one's only 2.1. This is only 2.1. So the difference in electronegativity is 1.4, right? That's a big difference in electronegativity. So here's what we do. We're going to represent it geometrically using vectors. I'm going to draw a little vector like this. Okay. in the direction that the bond is going, right? So I'm doing it like this because the bond is in that direction. And then the other one is going to look like this. Okay. Now, remember, the head of the arrow is the negative end, and the tail of the arrow is the positive end, right? So the hydrogen's down here, so we put the positive down there. The oxygen's up here, it's more electronegative, so we put the head over here, okay? Now the only question is, so we know the bonds are polar, definitely polar bonds. The only issue now is how do those vectors add up? If we were taking a physics course, we would calculate it. We would actually look at the x component and the y component of this vector, add them up and figure out what the net is. In fact, some textbooks even go through that a little bit. It's just an issue of trigonometry, right? It's just a triangle, actually. Because what happens is each of these vectors has a y component and an x component, right? So here's your x, here's your y. And then same thing with this one. There's your y, there's your x. And for those of you that have taken physics, what you do is you add up all the x's and you add up all the y's, and then you get your total out of that, right? But we're not going to do that in here. This is not a physics course, and it's not a physical chemistry course. It's a general chemistry course, so we don't need to go to that level. So we just sort of do it qualitatively. So imagine this way. Imagine, I like to use forces as the example because we all have experience pushing and pulling things, right? So imagine someone's pulling something in this direction and someone else is pulling on it in that direction. You're both pulling up, right? So if I'm going at it, you know, a diagonal, if I'm going this way, I'm pulling to the left, to the right, right? I'm pulling to the right, but I'm also pulling up, right? So if someone else at the same time is pulling that same object in this direction, they're also pulling up. Now they're pulling to the left, right? So they're going to the left and up. The other one is going to the up and to the right. So what'll happen is the left and right will cancel each other, right? The x component is gone, but the two are pointing up, so they're going to be additive up this way. So this is your net up, right? You're going to add these two together. And so when you add them together, they get like that. Essentially what happens is if you're in the same dimension, if you're adding y's together, it's scalar. You just add them numbers together. If you can get the x's together, you add those up together. It's a scalar quantity. So overall, what happens is you get this. You get a polar molecule, and I'm going to represent that with a vector that goes straight up. And it's larger than either of these two. It's larger than either of these two because it's additive in the y direction. So it goes up pretty large. So now you've got, essentially, I'll represent it this way. This is one way. You got a negative end here, and you got a positive end here. And actually what's interesting is that the negative goes right through the middle of the oxygen, right? It's right here. But the positive is actually in between the hydrogens. It's actually in between them. And so if you were actually to look at the geometry of the molecule is bent. So you got your hydrogen atoms here, but the actual dipole is through the middle of the molecule, right? So it's actually in between the two hydrogens. Often biology textbooks get that wrong. When you look at it in a biology textbook, you'll see that they show a positive on both the hydrogens. The actual positive is actually in between the two hydrogens, but that's a pretty advanced issue that we're covering here, okay? So now we know that if the molecule is bent and the bonds are polar, we've got a polar molecule. So that means that water is going to be polar, carbon dioxide is linear. Even though the bonds are polar, it's going to be nonpolar molecule because of the geometry, right? Of the opposite direction, just canceling each other. And so it's nonpolar. So that tells us that all we really have to do is two tests. One, are the bonds polar? If the answer is no, then the molecule is nonpolar. No question. If the answer is yes, they are, the bonds are polar, then we look at the shape. The shape will determine whether it's polar or not. And then it's a very simple thing. Now, there are some ways we can make it a little more complicated by saying, hey, what if the surrounding atoms are different and they have different polarities? Well, then that's going to affect things, right? But at least at the basic level, it's just, are the bonds polar? If yes, then you look at the shape. So what I'm going to do right now is I'm going to give you the lowdown on the shapes. So this is assuming that the bonds are polar. Okay, that's the assumption here. Again, if the bonds are nonpolar, then it's going to be nonpolar, no question about it. So here's what happens. Let's begin with our formula. Okay, these were the bent, right? So those are the bent. And the angles was 120, 104.5. Okay, these ones are going to be polar. Right, we just did water, so that's the example. So now the AX2E1, same situation. Because it's bent, they're going to add up additively in the y direction, so it'll be polar. Okay. The next one was AX3E. Ooh, I don't need to put a 1 there. Usually the notation is just put E. You don't put E1. Okay. This one was our trigonal pyramidal. Sometimes you put an AL at the end, sometimes you don't. This was 107 degrees. And this one's going to be polar. Okay, so that one is also polar. Okay, examples, H2O, NH3, and then this would be like SF2. Okay, that's one right there. Now let's look at some of the others. Some of the others were AX2 with no lone pairs. That's linear, 180. We already did this with carbon dioxide. It's nonpolar. Okay. AX3, Trigonal Planar, 120, nonpolar. Example of this, BF3. AX4, tetrahedral, 109.5 degrees, nonpolar. So that would be like CF4. AX5, trigonal bipyramid, remember this had two angles, 180 and 120, or 90 and 120, depending on which textbook you're looking at. This one's nonpolar. PCl5. AX6, this one was octahedral. This was 90 degrees, nonpolar. SF6. And then there was one more I did, which was AX4E2. That one was what I could square planar, right? That was the cisplatin, 90 degrees, nonpolar. So that was your IF4 minus. Okay, so take a look at that. How many of them are polar and how many are nonpolar? They're almost all nonpolar, right? A lot of molecules in nature are nonpolar, but the ones that are polar are really these shapes here. Those are your polar ones. That's why I put them at the top. The ones that are polar are the ones that appear to have only a couple or a few surrounding atoms and have lone pairs. So they have that in common, right? They have lone pairs. And the reason for that is that the lone pair screws things up. Essentially, molecules are symmetric. And so the atoms will kind of spread out, be symmetric and be equal, and it's nonpolar. Everything cancels out, right? Lowers things that way, lowers energy. But that lone pair messes things up. That lone pair pushes things away from where they would be because it takes up a lot of space. And so then that makes it a polar molecule. So the ones that are polar tend to be the ones that are bent and the ones that are trigonal pyramidal, okay? That's assuming, of course, that the bonds are polar, and it's assuming that all the surrounding atoms are the same, right? So what happens is if you have different surrounding atoms, the bond polarities don't cancel out, and so that it ends up being polar. So most, if you think about in biology, you've got molecules that are nonpolar, which tend to be the fats, right? The lipids, they tend to be nonpolar. They tend to be tetrahedral, carbon, carbon, hydrogen, hydrogen. And the tetrahedral, those will be, those are right here, tetrahedral, 109.5, those are nonpolar. Sugars tend to be tetrahedral also. However, they don't have all the surrounding atoms being the same. In sugars, one of the surrounding atoms is an oxygen, and the other ones are carbon and hydrogen. So when you have different surrounding atoms, those bond polarities don't cancel, okay? So let me show you some Alex problems here. There's really only one where you're doing in this section, and that is predicting whether molecules are polar or nonpolar. Okay. So this is Alex predicting whether molecules are polar or nonpolar. Okay, so in this particular example, they gave you 3 of them. They can do ions too. You can do ions. You treat it the same way. But here we go. Here's the 3 in this particular problem. Carbon tetrachloride, CCl4, fluorine, F2, and H2O, water. Okay, and you just need to know whether it's polar or nonpolar. And then they want you to tell you the atom that's closest to the negative side. It's an interesting question, okay? So let's take a look at the first one. Carbon tetrachloride, right? So here's how you approach it. Really what you have to do is draw the Lewis structure. Okay, now I'm just going to go ahead and give you the Lewis structure here because that's what you've been practicing in chapter 8. And you'll continue practicing it in chapter 9 if you're doing it. You want to be able to do Lewis structures like this, particularly if you're going to take advanced biology courses or pharmacology courses and stuff like that. It's really good to know these Lewis structures. Helps you with the molecular description of molecules. Okay, so here's our carbon tetrachloride. So it looks like we've got AX4, and that's tetrahedral. 109.5 degrees. Now, in fact, there is a big difference in electronegativities, right? Well, there's a difference, we should say. Chlorine has an electronegativity of 3, and carbon is 2.5. So there is a difference. It's not a huge difference, but there is a little difference. But it's tetrahedral, right? Tetrahedral is in that table. That's nonpolar. And here's why. I'm going to try to draw this for you. It's 3-dimensional. If you have a tetrahedral, here's our central atom. You have a dipole like this, right? Remember, this is more electronegative, the chlorine is, so the arrow is going to point towards the more electronegative atom. Right, so there's your chlorine. And then, remember, this is 3-dimensional. Tetrahedral is kind of a tricky one. So then you have a vector coming this way, and there's your second chlorine. And then you have a vector coming out of the plane, out of the board of what you're drawing on, so toward you. And then you have one that's going away from you. So it's like a little pyramid, right? And so what happens is this is not a simple it is a simple geometric problem, but it's not one that we need to go through the calculations for. You have to be pretty good at trig to do this, or at least decent at trig. It's three-dimensional, so there's X, Y, Z. So essentially what happens is this one that's coming out of the board here is only coming out of the board a little bit. This one over here is going into the board a little more, and this one's coming out of the board a little bit. So essentially coming out of the board, these three cancel. This one up here is not coming out of the board at all. It's going straight up, like on a flat piece of paper. So it doesn't even have a component coming in or going out. So overall, coming in and out of the board, they cancel. This one up here is straight up, so it's not going to the left or right. So it's not going this way or that way. This one's going pretty far this way. This one's only going a little bit this way, and this one's going a little bit this way. So these two cancel this one. And then X, up and down. These ones are coming down a little bit, all three of them. This one's going up a lot. So they cancel in the Y direction as well. So overall, they all cancel out. You have to go through the trig to figure it out. But it turns out tetrahedral, that's what happens. So this one, nonpolar, right? It's nonpolar because they cancel out. It's a tetrahedral, okay? The atom closest to the negative side. Well, there is no negative side, right? There is no negative side for this one because overall it's nonpolar. Okay. Yeah. Now let's take a look at the second one. The second one is F2. F2 is so we don't have to put anything there. F2 is a little easier. And here's why. I'm going to draw the Lewis structure. Okay. This is simple. They have the same electronegativity values, 4.0. So what's the difference in electronegativity? It's 0. So if there is no difference in electronegativity, it's nonpolar immediately, right? The assumption that we made in this whole discussion was that you have to have a difference in electronegativities for it to even be polar, right? So this one's nonpolar because there's no difference in electronegativity. We didn't have to take into account shape. If there's no difference in En, then you don't have to worry about the shape. Water, we already know the answer. We know it's polar, right? Water, pretty simple. Here's your Lewis structure. We figured out it's AX2E2. So that's bent 104.5 degrees. And we also figured out already that each bond is polar. There's a big difference in electronegativity. So you have two vectors pointing in this direction. So it's polar. Water is definitely polar. Which atom is negative? The oxygen, right? The oxygen is the negative. It's the more electronegative atom is the one that's negative. So it's going to be the oxygen atom. Okay. Let me see if there's any that are different here. Okay, so now this one's a little trickier. So I'm glad that we have this one. We have CH3Cl. That's a little trickier. And then we also have CH2O. This example also had F2, but we don't need to worry about that. We just did F2. Okay, so let's take a look at these two. Now here's the, I don't want to call it a trick. It's not a trick, but it's something we have to consider. Notice that when we do a lot of these, carbon is the central atom, right? So what I'm going to do is I'm going to begin with these. Again, we're just trying to determine whether it's polar or nonpolar. It turns out both of these are polar. The issue here is, let's start with the Lewis structure. So I'm going to start with CH3Cl. Remember what we said yesterday. If you have carbon, put that at the center, and then just draw everything else around it. Okay, so put carbon to center. Carbon is the central atom in nature, right? That's what makes it such an amazing element. It's always a central atom. Okay, you're never going to see something like this. So you see here where I put carbon as a surrounding atom around the oxygen. You don't see that. It just doesn't really happen. Carbon is the central atom. Okay, so I'm going to finish out the Lewis structure. It's a pretty simple Lewis structure. You know, Lewis structures were really invented for organic molecules. They work very well with it. So here we go, CH3Cl. Okay, so now we have 3 elements. That's what makes this more interesting. It's a more challenging issue. If you look at the electronegativity values, this one's 2.1, this one's 2.1, this one's 2.5, and this one's 3.0. Now, don't worry if you get slightly different values. I know some of the online values are a little different. Like they might put chlorine as 3.1. They might put hydrogen as 2.2. You know, essentially there's some difference, right? But really we're just looking at qualitative values anyways. So here's what happens. Let's do our geometry. Central atom is carbon, and there are 4 surrounding atoms with no lone pairs. So that's AX4. Remember, we talked about this very briefly yesterday. If you have different surrounding atoms, in terms of the shape, it doesn't matter. They could all be the same element, all hydrogen, or one of them's chlorine, one of them's, the shape is not affected by what the surrounding atoms are, as long as they're surrounding atoms. Tetrahedral. 109.5 degrees. Now be careful, because if these were all chlorines or all hydrogens, it'd be nonpolar, just like we looked at earlier. Tetrahedral is nonpolar. However, what happens is when you have difference in electronegativities, so this one's 2.1, but this one's 3.0, they don't cancel each other, right? They only cancel, remember, if I have 2 forces go in the opposite direction, they cancel each other if they're the same size. 50 pounds of force, 50 pounds of force, they cancel. If I have 20 pounds of force and 50 pounds of force, it's going to move this way, right? So they only completely cancel if they're equal. So these are not equal. These are different electronegativity values, okay? So here's what we have to do. We have to say, look, we have a vector going this way, right? So here's your carbon, here's your hydrogen, this one up here. We have a hydrogen over here, so I'm going to draw it out here. Okay. There is a difference in electronegativity, right? 2.1 and 2.5. So those 2 are going in those direction. Okay. Now we also have a chlorine, so I'm going to draw the chlorine this way, but look what happens here. For the chlorine, the vector goes out this way, right? It comes out toward the chlorine because the chlorine is 3.0. The head goes toward the more electronegative element. And then the other one is this one. There's your hydrogen. Okay. So now you have to ask yourself, well, what's going to happen now? By the way, it doesn't matter where you put the atoms. If I'd put the chlorine up at the top, you're going to get the same answer. If I'd put it on the right, you'd get the same answer. So don't worry about that. Here's what happens. You can kind of think of it sort of like, in a way, these 2 are canceling each other, right? Because they're sort of on approximately on opposite sides. But this one's going down and this one's going down, right? So 2 of them are going down. None of them, I mean, this one's going up a little bit. This one's going up a tiny bit, but this one's going down and this one's going down. So overall, what you get is the most electronegative atom is the chlorine. And so it's going to be the negative end. So you're going to get a negative here. Okay. Where's the positive going to be? It's a little complicated because of the way these things add up, but it's going to be somewhere around here. The positive will be up there. Okay. So our answer then would be that it is in fact polar, and that the electronegative atom, that's the chlorine, is going to be the atom that's negative. Okay, so there's your negative atom. And then there's the question of whether it's polar or nonpolar. So when you analyze these, you really have to kind of go a little deeper into it. Let's try the CH2O. carbon again at the center, oxygen, 2 hydrogens. Okay, I just draw everything around the carbon. Now, here's a little tip. If you saw something like this, CH3OH, see how the H here is after the oxygen? When they put the hydrogen after the oxygen, that means it's attached to the oxygen. So this would be CH3OH. So with the hydrogens after the oxygen, you attach it to the oxygen, right? But if it's just CH2O, the hydrogens and then the oxygen, everything's going to be around the carbon. Okay. Okay, let's do the Lewis structure. Carbon is in group 4A, hydrogen's in 1A, and oxygen's in 6A. So you got 1 plus 4 plus 1 plus 6, 12 electrons. Okay. We've already used 6. So we're down to 6. So let's put them on the surrounding atom first. And then carbon only has 6, so we're going to have a double bond. This is called formaldehyde, by the way. Yeah, should be consistent. Okay, so there's your Lewis structure, right? -6, we're down to 0. Okay, so there's your, so now here's what you do. We've got a carbon in the center, so that's A. It's got 3 surrounding atoms, so that's AX3. No lone pairs, so that's trigonal planar. All right, 120 degrees. So I'm going to draw the structure, the geometric shape, and then we'll consider polarity. So this is all practice for 9.1 also, right? Because you have to do the shape to figure this stuff out. So here's what you got. You got trigonal planar. So you have a carbon, you got your oxygen up here, and then you got your 2 hydrogens down here. And your angles are 120. Right, it's a little flat, like a little propeller, okay? It's flat, trigonal planar. Again, it doesn't matter where you put the oxygen, where you put the hydrogen. It's not an issue, okay? Also notice I didn't put the lone pairs because we're not interested in the Lewis structure. We're trying to figure out whether it's polar or not. So let's not worry about lone pairs and all that stuff. Okay, how do we deal with this? Well, trigonal planar we learned is nonpolar, but that's only if the surrounding atoms are identical. If they aren't the same and there's differences in electronegativity, it's going to be polar because they're not going to add up perfectly. And I'll show it to you for this one. This one's 3.5, this one's 2.5, this one's 2.1, and this one's 2.1, right? So let's draw the vectors in. We've got a vector that's kind of small, right? Because that's not a very big difference, 2.1 and 2.5. So it's a little polar, right? That's a slightly polar bond. Same thing with this one. It's a little bit polar. Okay. But now you've got a much bigger difference between the carbon and the oxygen, right? 3.5 and 2.5 is a big difference. So that's a big, in fact, I probably didn't even draw that big enough. Woo, right up there. There we go. So there's your difference in electronegativity, 1, right? So remember, the bigger the difference, the more polar it's going to be. Okay. In fact, if it gets above 2, it's ionic. So how are these going to add up? I hope you can see this geometrically, how they're going to add up, right? This one's going up. It's going up a lot, right? This one's going up a little bit too. And this one's going, they're all going up. Now this one goes a little bit to the right. This one goes a little bit to the left. So those will cancel. The left, right will cancel. But overall, they're all going up. One of them is going up a lot. The other ones are going up a little. So in terms of the y, it's much easier if you'd taken physics, right? Because then you would be able to just do this mathematically. But in terms of adding them up in the y direction, 2 of them, oops. Well, let's do it this way. 2 of them are going up a little bit, and one's going up a lot. So if you add those three together, you're gonna get a large y direction, right? So that's exactly what happens with this molecule formaldehyde. It's actually a very polar molecule. And the negative, remember, the head is the negative. So the negative is up here. What atom is that close to? The most electronegative atom. So if you're ever in doubt, if you want to know which atom's negative, it's the atom that has the high electronegativity. So if you have an oxygen, it's going to be the oxygen. If you have a nitrogen, it's going to be a nitrogen because those are electronegative. Okay, you're not going to be it's not going to be hydrogen. Hydrogen is a much lower electronegativity. So the answer here would be yes, it's polar. Now it's sort of, and the electronegative atom is the oxygen. The oxygen is going to be the atom that's negative. But geometrically, it kind of looks like this. It's a little bit similar to water. It's polar in this direction. And then you've got your hydrogen, your carbon, your oxygen, and your hydrogen here. So those are the bonds, but the polarity is in this direction. It actually goes like this. So technically, they don't ask you this, but if they said where's the positive would be essentially on the carbon, right? It's sort of right here. Maybe a little bit below it, down here. They're not going to ask you that. That's a more difficult issue. But the negative is definitely going to be on the oxygen. Okay.
And the positive, it's always on the bottom, or it's in the middle?
The positive is going to be, so remember, we're talking about a dipole, right? So a dipole is just a straight line with an arrow, with a head and a tail. So if you figured out that the negative is up here, the positive is going to be down here, right? So the question is it always? Well, it actually depends on how you draw the molecule. Suppose that I'd drawn it this way. Someone might draw it that way, right? There's nothing wrong with that. So now what would happen? Now you go this way, right? So now the negative would be here and the positive would be up here. Okay. So the answer is the positive is going to be on the opposite side of the arrow. So if you figure out where the negative is, which is the head, the tail is going to be the positive. And that's going to tend to be near the more positive atom, right? The more positive atom is where the positive charge is going to be. Okay. Yeah, good. Okay, so just looking at these, there's really what they do is they give you 3 each time. And one of them is generally nonpolar because it's 2 atoms, the same element. So that's nonpolar. And then they're going to give you, one where all the surrounding atoms are the same. That's nonpolar because they're going to cancel. And then one where you have different elements. And those tend to be polar. But go through them. That's 9.2. It's really only one type of problem you have to do. And then next week, I'm going to go over hybridization on Tuesday. And then on Wednesday, I'll do molecular orbital theory. And those will be the last 2 topics from chapter 9. I might even take a little bit of Thursday to kind of go over it a little bit more. It might take 2 days to do the hybridization, but I suspect not. I think it'll just take 1 day, but we'll see. So I'll see you on next Tuesday if you want to do more bonding. Hybridization is important, and actually these shapes, all this geometry, this is really important for organic chemistry if you ever want to take that. So if you're a pharmacy major, pre-med, pre-dental, physician assistant, you definitely want to kind of practice all this stuff from chapter 9. It's important stuff. If you want to get your DPN or DMP, eventually make sure that you do this as well, because all this bonding stuff is important when you go on to take biochemistry, pharmacology, all of that kind of stuff, okay? If you're gonna do occupational therapy, probably not as important, but it's up to you, okay? If you're a chemistry major, for sure. All right, you guys, so take care, and it's a long weekend, right? It's a long weekend, so I will be working on this stuff on Tuesday. I'll see you then. Okay, take care.
Thank you, Professor.
Thank you.